Hello, and welcome to the second video of the FP2 chapter Polar Coordinates. Quick review on the screen to go through what we did last video. Convert these polar functions to Cartesian equations. Start with the easy one over here. We know that this is going to give us a circle, so we've got x squared plus y squared is equal to 25, and that comes from squaring both of these, and then remembering that r squared is equal to x squared plus y squared. Next, we've got these two here, very similar. Put these into their usual forms for sine and cosine, and then rearrange. So we've got r is equal to 4 over cos theta here. So r cos theta equals 4, and we know that r cos theta is the same as x. Similar idea up here. R sine theta is equal to y. Over here, a similar idea again, put it into sines and cosines so that we can get one of these or both of these, and then we can convert these into x and y respectively. So cot theta, that's cosine theta over sine theta. Cosecant, so there's another sine theta on the bottom there. Take both of these sines on the other side. So we've got r sine squared theta equals cos theta. And then to get r cos theta, we're going to have to multiply both sides by r, which is good for the left-hand side as well, because we've got one r sine theta here, and if there's another r, then we've got r squared sine squared theta, which is y squared. So multiply both sides by r, gives us y squared on the left and x on the right. I referred to these as basic polar functions in the last video, because in this video we're going to convert harder polar functions into Cartesian equations, but it's a very similar idea. We're still using these four things here, but this time, in order to convert polar functions of the form r equals sine n theta or cos n theta, we need to use some trigonometric identities as well in order to make this or this something that we can turn into r cos theta or r sine theta. These are still the things we're aiming at. And if we've got powers of r, then we can use this to help us with that. So for example, r equals 2 sine theta. First thing we should do is to manipulate this to give us something we can substitute for x or y. So initially we're going to use an identity here. R is equal to 2 sine theta cos theta, using the double angle formula. And then because I don't have r sine theta, just sine theta, I'm going to multiply by r. But I'm also going to multiply by another r here to get r cos theta. So I'm going to multiply both sides by r squared, which gives me r cubed on the left. And I'll put one of those r's in front of the sine theta, one in front of the cos theta, just to make it clear why I've done that, so that this and this can turn into y and x respectively. So this gives me 2xy on the right hand side, and then on the left hand side I just need to substitute out r with whatever indices are necessary in order to put it into this form here, x squared plus y squared. So if we've got r cubed here, I can write that in terms of r squared just by putting it in a bigger bracket with an index 3 over 2. So that can now change into x squared plus y squared to the power 3 over 2 is equal to 2xy. So a quick recap, used an identity first to break this into sine thetas and cosine thetas, multiplied by enough r's to get an r sine theta here and an r cos theta here, so we could change those into y's and x's. And then the consequence of that was we had a bunch of r's on the left hand side, and you just need to manipulate the indices to get an r squared in a bracket, and then whatever index is on the outside there is just the consequence of what you've done so far. So I've got a few more examples of these, possibly more than you need. So if at any time you think, yes, I've got this, I don't need all of these examples, please do skip ahead. But I'm going to do each of these in turn, just in case you need them. R equals cos 2 theta. The identity for cos 2 theta is cos squared theta minus sine squared theta. And then that's r equals, but I'm going to need r squared to put here with this cos squared, so that r squared cos squared theta can change into x squared, and I'll need an r squared sine squared here to change this into a y squared. So I need r squared on this term, r squared on this term, so I need to multiply the bracketed expression on the right here by r squared, so on the left I need to multiply by r squared as well. Let me write that out. What I'm doing here is this. In order to get this. And then the powers of r and the powers of the trig ratios match, so I can change that into the powers of x and y respectively. For some reason I've got an r squared there. That should be an r cubed because it was already an r. Sorry about that. But now, again, as with the previous example, I can change that into r squared with the appropriate index on it, so that I can change it into x squared plus y squared to the power of 3 over 2. Taking it a step further, r equals sine 3 theta. Using the addition formula, we have sine theta cos 2 theta plus sine 2 theta cos theta. And then, of course, we have to put the identities for the double angle formulas in here and continue expanding this out. So we've got r is equal to sine theta times cos 2 theta, that's cos squared theta, minus sine squared theta, plus cos theta times 2 sine theta cos theta. And all of that gives us 2 sine theta cos squared theta from this term, and a sine theta cos squared theta from this term. So we get 3 sine theta cos squared theta. And then from this term we also have a minus sine cubed theta. So in this case I'm going to need r cubed on the right hand side to match this, so I can turn this into a y cubed. And an r cubed here, 1r here for the sine theta, and 2 of them here for the cos squared theta. So I'm going to multiply everything by r cubed, giving r power 4 on the left. 3r sine theta if I split my r cubes up into r and r squared here to make that clear why I've done that. And the r cubed there with the sine cubed theta. So the r sine theta here becomes a y, r squared cos squared theta becomes x squared. I usually write my x's first, minus y cubed, and on the left we get x squared plus y squared all squared, because obviously r to the power 4 is r squared squared. So that is our third one. The final one is very similar. R equals cos 3 theta. The identity here for cos 3 theta, we're going to use the addition formula again. For cos is cos theta cos 2 theta minus sine theta sine 2 theta. Applying the double angle formulas, we get cos theta cos squared theta minus sine squared theta minus sine theta times 2 sine theta cos theta. This time we have 2 sine squared theta cos theta, and it's a negative. And over here we have another minus sine squared theta cos theta and a cos cubed. So it's very similar format, but subtly different. We get cos cubed theta and a minus 3 cos theta sine squared theta. And on the left still r. Multiply everything by r cubed. And put one of those here on this term, and 2 of them here. And we have x squared plus y squared squared equals x cubed minus 3xy squared. Depending on how complicated your original formula is, how many identities you might have to use, these can get a little bit involved, but it's a very similar process each time. So we've got a few examples to finish the video. Find the Cartesian equation of these curves here. First one we know already is going to be a circle, so we've got x squared plus y squared equals 16. The second one we can see we're going to need an identity here. R is equal to 2 plus 2 sine theta cos theta, and as we've just been saying, I need an r sine theta here and an r cos theta here. So I need to multiply all of this by r squared, which will give me r cubed on the left, 2r squared plus 2, and I'll put one of them with the sine and one of them with the cos. And then we get a manipulation of indices to give x squared plus y squared to the power of 3 over 2 on the left. And then we've got an r squared here, so that's 2 times x squared plus y squared. And then plus 2 times r sine theta, which is a y, and r cos theta, which is an x. So we've got an xy there. The last one, we've done most of the work already in a previous example. We've got r squared equals cos 2 theta, which is cos squared theta minus sine squared theta. Multiply everything by r squared gives us r power 4 equals r squared cos squared theta minus r squared sine squared theta. And then we've got x squared plus y squared all squared is equal to x squared minus y squared. So we have quite a few examples there of changing polar equations into Cartesian equations, but you also need to be able to change Cartesian equations into polar equations. Now this is not quite so difficult. Whether you found that difficult or not, this is easier because all you need to do is substitute y equals r sine theta and x equals r cos theta everywhere you see a y and an x. So this first one here, we've got r squared sine squared theta for y squared equals 4 times r cos theta. Now depending on the question, you might have to rearrange this to make it look like a certain thing. For example, here you could turn this into a tan and a sine on the left, or like we had in the starter question, a cot and a cosecant on the right, and you could simplify by cancelling one of the r's. But unless the question tells you to do that, I wouldn't worry too much about manipulating these. That is in polar form. Part B, same idea. Anywhere there's an x, replace that with an r cos theta. So we get r squared cos squared theta here. And with a y, r squared sine squared theta for y squared, and that has to equal 5. Same again, you could manipulate this, you could factorize out the r squared if you wanted, but unless the question tells you to do that, I don't think it's worth doing. Third one, y is equal to r sine theta times root 3 is equal to r cos theta plus 4. So changing from Cartesian equation into polar equations is generally much easier. Changing from polar equations to Cartesian equations can require a little bit more work because you need to manipulate to get one of these things. So you can substitute out to get x squareds, y squareds, x's and y's. And that should be enough now for you to have a go at the questions in exercise 8a. And maybe I'll see you in the next video.